Yes, well, thank you, Peter, for the invitation. Good afternoon, everyone. My name is Shadi Atia, and this work is not representing myself. It's actually representing a team, and literally it was a team. It's a collection of different ideas and thoughts, and a lot of effort to come up with a definition that cater for us as building professionals, regardless of the specialization. So in this context, we have several authors collaborated within the IEA context, and we wanted to have a definition for resilient cooling. And before starting, I would like to confirm that I can share the slides with you if you would like to have them. And the original paper is accessible for free from the link and the QR code in front of you. Later on, I guess Philip will make the presentation available if you wish to download the paper. So the main question that we wanted to answer is mainly what are the existing concepts of resilience, because resilience is represented in different fields. It's represented in the field of behavioral, psychological behavior. It is in the engineering field, on the urban scale, structural engineering. But when we look at the building engineering field in general, almost you cannot find a definition for resilience because the scale of buildings is too small in regard to the concept, because the concept of resilience has a relation with a scale which is related to a big impact of a disruption. So this was the first question. The second question was how to define resilient cooling for buildings. So in this context, the methodology that we developed was based on consulting the literature found on the international scene. And as you can see, there is not many active countries working on resilience in Europe. We are lucky because even though we complain about climate change, we cannot compare the situation with other more sensitive countries like Chile, the west of the United States, or the North America in general, Australia, and if you remember the fires, and the different droughts, the earthquakes, and so on. So we opted to expand our research, and we looked at the United Nations publications, and we got in contact with the experts of the UN resilience task forces. Also, we looked at the IPCC work group on vulnerability, and also we checked all IEA previous publication and the United States Green Building Council and the RELI rating system. So this was the overall literature. When we look at the final government, the summary, when we look at the new IPCC report, this is a sneak preview for the new IPCC report that will be published most probably the last quarter of 2021. There is a new definition of the different climate change scenario. And as you can see, there is a different characterization of the different disruptions that might impact some regions across the world. And one of the most underestimated disruptions are fires. And this would be the threat number one in Europe in association with drought. For sure, overheating is another threat, but as you can see in this graph, there is a series of different disruptions. So it was very difficult for us to define resilience without making sure, okay, what is the disruption we are talking about? Because at the end of the day, resilience is a response to a disruption. So this was the first glimpse that helped us to define sharper our scope. And definitely we learned from this development or from this paper that we must define the disruption, and we must define the scale of the disruption and the time of the disruption if we want to define the definition of the resilience. Because the definition of resilience is really, in our context, would be vague term. And what we are trying to present in this paper is one of the first or earliest concepts or proof of concept. So this is not a definitive work or a conclusive work or a comprehensive work. It is one of the thoughts that we are throwing in the lake of ideas. So it's important to take the message also like this is not like a final or a one-shot work. So one of the most important factors when we started to characterize resilience, we discovered that there are 4 features that are very important, and they are very strongly associated with any risk factor related to overheating in buildings or power outages. It's mainly the vulnerability of the building, which means that the sensitivity of the building even prior to the shock to be exposed to overheating problem and thermal discomfort issues. The second important factor was the resistance. So how can the existing building, including the existing HVAC system, whether the building is free running or is the building mechanically conditioned, how long can the building resist the phenomena? In this case, the phenomena will be overheating or a heat wave. And then the third aspect would be the robustness, because this was a very difficult term. Robustness has to do that you get a series of continuous shocks until you fail. And then it shows how you recover back from the failure, actually. So therefore, we had this term of robustness and recoverability. And as you can see in the graph, we discovered that those are four main concepts or sub-concepts that must be associated with the term resilience. Otherwise, it would be very difficult to distinguish the term resistance and robustness. So the definition of resilient cooling of building involves those four criteria, mainly vulnerability or sensitivity to risk, resistance or the absorption of the shock, robustness, which is the adaptation after failure, and here we need to see the flexibility and the plan Bs or the contingency plans, and finally the recovery in the sense of period and remedy and the curve of recovery. So these are the four factors that help us to come up with an overall definition or view on what happens with a building to define it as resilient. So as you can see, this complex graph shows mainly that a building before having exposure to any shock will have a certain performance. If you follow this blue line, the dark blue line, before the shock, and then once there is a shock or a disruption, we will have a resistance. How long it will resist depend on the period, on the intensity, on the severity, on the preparedness of the building in general, or its design simply. And then we can have a failure or a reduction of performance, but still the building is resistance. And once we witness failures in the performance, such as a power outage, the cooling system is not delivering anymore, any shutdown in the system, any reduction in the failure of comfort conditions beyond the tolerated or legal thresholds of performance, then we enter in the third phase of robustness, where we witness a failure. Once the building is exposed to this shock and failed, then we can start after that to measure how it can recover back. And those four stages or phases that a building will go through, including its occupants and its equipment, they will define its resilience. So this was the complexity to bring up this concept, and we saw that the robustness is the threshold between resistance and recovery. So it was very important to check and correlate it with a timeline of events. So as if there is a crime or something, but it's not here a crime, it's a crisis or a failure, and you must link it to the timeline and check how is the system looking to react to this disruption in relation to the design conditions, the pre-shock design condition, the minimum requirement of performance, and the critical requirement of performance. And if the building goes beyond the critical requirements, then it has a failure, and then depending on its ability to bounce back, actually this bouncing back feature or ability is very important to define a building as resilient. So this was the complexity of the term and the association of failure with the term. Maybe now, why did we decide to focus on power outage and overheating? This was, like Peter was talking, this was a decision made by consensus because we opted to this decision. We were in the year of Corona. Some people pushed us to put Corona as a disruption. It can be, and it is a disruption, but in this case, we are talking about air quality. But any example you want to take, you can apply it to this case. It can be Corona, COVID, air contamination. It can be a fire outbreak. It can be an earthquake, whatever. So in our case, we focused on overheating and power outage, and we found those are the most relevant to our Annex 18. Now, some final words, because the time is running, and I want to respect the 10 minutes given to me. and maybe if you have any interaction. In conclusion, we must not forget that the difference between the term resilience and resistance and robustness has to do with the exposure to shock and the failure. If a building fails, then after that, and it recovers back, then we can call it a resilient building. But if the building does not fail, it will remain under the realm or the definition of resistance and robustness. So this is very important to take into account, that failure is a must to call something resilient, and this ability to bounce back. Any definition of resilience must be based on the identification of the specific shock or the disruption that it needs to be resilient against. And designers must specify and distinguish the resistance and robustness conditions against heat waves and power outage events. So the resistance period involves the building ability to resist the shock with the same pre-shock operation conditions. And this was also tough to define. Number 3, resilient cooling design is an urgent requirement for future-proof buildings, and weather extreme must be anticipated to assume well-being. So if we are assuming that a building, we can label it as a resilient design building according to the RELI, the American or the United States Green Building Council's rating system, we must already have this anticipation aspect, and the vulnerability has to be assessed in advance, and the recoverability should be also measurable and embedded in the design process and in the performance and the key performance indicators associated with the building. Number 4, building operation systems in this case and building management system will play a significant role in applying the adaptation strategies, because still the definition of resilience can be applied to fully passive buildings or free running buildings, but most probably if we want to maintain a certain comfort condition, we will have also to rely on automation or automated system, BAS in general, so that they can help in the risk mitigation in collaboration with building users. It can be simply we can only rely on occupants. That can happen. Imagine a school without a system. There is a shock, there is a failure, and we only rely on occupants, but we assume that to call a building really resilient, we cannot only rely on occupants, especially if it's a large building or a commercial building. And finally, resilience is a process, so the criteria should be addressed integrating user experience during shocks. So it's essential to increase the emergency learnability and look at real case studies with real situation in order to feed the preparedness loop and inform designers about how to design the building in a resilient way. I think that's ending up my presentation. I'm available, the paper is available, and I would like to give space to others, and I would like to remind that this is a collective work, including a series of authors, and we are looking forward that with Peter, there's a KPI group that will work now to translate these stages or associate them at least with key performance indicator. Thank you very much for your attention, and I'm available if you have any questions.
Thank you very much, Shady, for this presentation.